Thanks everybody for joining. And I'm going to just start moving through the slides. Hopefully we cover everything. It's a very in the weeds topic, getting into performance paths. And today, here's the additional AIA info. Just leave that up for a second and then jump forward. So description of the webinar today was, looking at energy code requirements, specifically performance path routes. And so there's your regular building performance compliance, and then we have ERI pathways. I'm going to focus mostly on the simulated performance path of those two, and get through these learning objectives. And I think we've done a pretty good job. This was Brian and I met together, just sort of how to keep the content out of the weeds on the performance path conversation. But we're going to look at the various energy code pathways that can be permitted under the UCC, simulated performance and ERI, look at performance and cost implications of electing to pursue a performance pathway, and then try to apply that to sort of future code implications, which is very interesting, and especially with us approaching adoption of a new code cycle. So just a really quick background on me. I've been in this for several years now. It's been a commitment of mine for going on the past 15 or so. But my background has been, in building science and high efficiency buildings. I've worked in a number of places, and, HVAC background. So I really enjoy this work. I broke the agenda down in this way, where we're going to look at the pathways first. The focus is going to be the R405 section of the code, which is the performance or the total building performance or simulated performance path. I'm going to look at pursuing this performance by stage of construction when we get into the nitty gritty part, and then sort of at the end, discuss some future code implications. I did my best to flag areas along the way that sort of we'll talk about as the future implications. So just as like a really, really into the past, what we've done as we pursue these changes. Many of you probably remember when we first looked at the 2015 I-codes back in 2018. I was able to do a presentation actually for PHRC then on, what does it look like trying to reach this new, what's going on with the blower door test? What's this all about? We have to do some additional testing back then. That was the big move. But that was back in 2018 when we moved out of the 2009 into the 2015 I-codes. And then, as you know, just this past cycle. So here's the 2018, the 2009 to the 2015 I-codes when we made that change. And then most recently, in 2022, we moved from the 2015 to the 2018. And, this is where we went from the amended 5 air changes down to 3, among a number of other changes, including some to the prescriptive table. One interesting thing I wanted to point out on our last code is when you go to energycodes.gov and look at, the larger landscape of code adoption throughout the United States, it indicates that PA, when we went through this code cycle, we took on the 2018 IECC with amendments. And with those amendments, we're still basically pursuing the 2018 IECC. It's just a little bit less. It says it's a little bit less than the 2018, but only by less than 1%. This next code cycle that we are getting into, so that's where we're going from the 2018 to the 2021 codes. And that's under deliberation, like coming up now. Like this is a hot topic. And Brian and I talked about this a little bit and wanted to just make note that the 2021 has not been adopted yet. It's wouldn't go into effect until 2025. So that would be our 2025 code change. But keep in mind the review and advisory counselors beginning that deliberation now, and Brian pointed out, so it's not too late if you want to let your voice be heard. But what is possible, and I'm not speculating on what will happen, and definitely not, no idea what we actually adopt. But if it's similar to something in Virginia, you would see something where, and I just made a note from this same website, but it's like, yeah, they went through the 2021 adoption, but it's actually more similar to the 2018. In fact, almost 13% less efficient than the 2021 adoption. So these are the kind of things that happen through the amendment process. And it's just important to know that we really don't know what's coming in the 2021 adoption cycle that we'll see next year. So just wanted to point that out. Even farther into the past, I think this is interesting just to note, but like energy code's been around for a long time. Like back in, this is probably from late 70s to mid 80s there, and into the 90s, where we had CABO, which was a Council of American Building Officials, BOCA, another building official organization, and the model energy codes. But all of these books reference more than one path beyond prescriptive. There's always been alternatives. When we've moved into the I codes, this is where they've become a lot better structure, and the guidance is more clear on how to pursue those pathways. But like in poking around for this, I mean, it goes back even farther. Like into the early 70s, there was some research, and this was one of the earliest books I could find, something called just the Residential Energy Conservation book. The earliest copy I found was 1977. So it's been around for a while. But now here we're going to focus on our current code in Pennsylvania, which was the 2018 adoption, which was slightly amended, excuse me, but only by 0.6% less than the 2018. So it's pretty close to the 2018 code. And under the compliance section, you'll see this R4012, you have some pathways. So you have to choose, here's a couple doors for you. You can go this R401 through 404 option. You can do R405, which is this simulated performance that I'm going to discuss in a little more in depth today. And then 3, another performance path, which is this energy rating index path, that's R406. So just to look at these approaches a different way, you can break them down like this. There's basically one way is a prescriptive route, one way is a performance route. The prescriptive paths focus on piece by piece what has been prescribed as the minimum requirements. So your walls, doors, windows, ceiling. You can use an alternative, including like a total UA, which a lot of folks are familiar with, which is a res check, which allows you some trade-offs. And then another path is the PHRC, and the UCC allows for the PHRC to help develop the PA alternative, which is another prescriptive type path. On the performance path, we're looking more at overall, how does the home perform as a system and its overall energy performance? And those are represented in the code under sections R405 and R406. The real difference in the math that's happening in the background is, I'd like to think of like these trade-offs in the res check and the total UA that you find in the prescriptive path to be sort of like calculated averages of the values, where when you get into these performance paths, it's actually simulating the energy use of the house over the course of a year. So the simulation takes into account, our climate zones, heating and cooling degree days, and holds that against the whole house as a system. How's the envelope performing with the ventilation, with the heating and cooling, the space conditioning systems. And when you get into the energy rating index path, you're including more things. So I found this is actually a childhood book of mine, and I realized it's probably where the curse of enjoying reading code books was first adopted by me, was these choose your own adventure books. And it's really held true. So I'm going to keep coming back to this theme that the energy code is a choose your own adventure. So let's start our adventure, shall we? So here's the 2018 and these two primary pathways that I'm pointing out: prescriptive path or performance path. And under prescriptive, you see we have the straight prescriptive plus these UA alternatives, which are averaging and total UA approaches. And then on the performance side, we have simulated performance and the energy rating index. So that's 5 things. Oh yeah, this other prescriptive one, the UCC's PA alternative, or which is PHRC's, but it's allowed under the UCC. We just didn't want to make it seem like the PA alternative is under the 2018 IECC. It is not. It's under the UCC. But hey, it took me this slide to make these appear in this order was probably 30 minutes of preparing the presentation. So we're going to focus on these 2, 4, and 5. And most specifically, I'm going to be looking at R405. And just for a quick discussion, before we dive into some of the specifics, is that both performance pathways have backstops. So in the 2018, when you hear backstop for the simulated performance, it goes the whole way back to the 2006. And I'm going to expand on this a lot over the next several slides. But when it says backstop, it's meaning, yeah, you have flexibility for trade-offs in your compliance pathway. You still can't get so creative that it's worse than the 2006 IECC prescriptive when you're using this section R405 for simulated performance. And currently, when you're pursuing the energy rating index, the ERI path, that one has a backstop of the 2009 IECC prescriptive values. So we're going to talk a little more in depth about that, but the flexibility in these pathways comes from, as long as you can show that your overall energy use is greater than or less than or equal to, if you had done it to the current prescriptive path, you're allowed to trade off things the whole way back to the 2006 for the simulated performance and to the 2009 code for energy rating index. So there's a lot of similarities, and this goes the whole way back through all of those books that we were showing, back into the residential energy conservation book, through the CABO and BOCA and the model energy code books, and into the IECC books. All of those choose your own adventure stories have something similar, besides there's more than one path. And it's that they're all focusing on efficiency of the building. They're all looking at, are we achieving this efficiency and keeping the building a durable building? And is it still a healthy building? So these are all similarities that you're going to find in all the paths. Some differences between prescriptive and performance is the way I've kind of come to look at it is, I think of the prescriptive path as being like, this is more about labels and tables. Like I have a table that tells me what labels I should expect to see when I walk into this house. So it's mostly about labels and tables, where the performance path is coming down to how things actually perform, their tests and measurements and installation verification. And I'll talk a little bit more about that. But on the code enforcement side of things, and maybe this is a good place to just briefly mention something for the code officials. We're going to be talking in the next slides about everything's about the reference and the design. So you are designing or proposing for a home to perform a certain way. And sometimes the performance is where you're saying you are exceeding the bare minimum. So this is why the testing becomes important. And it's not just testing at final. It's important, hugely important at the pre-drywall stage of construction, because there's so many details to verify, some of which aim toward the distribution system of the duct, the R value, the insulation of the duct, quality of the installation of the insulation that can change its grading. And all of those things impact and are reflected in that comparison between what's in the reference compared to what's proposed. And when you go these performance route, all of those, you should be proving all of those things along the way with documentation, the grade 1 insulation, things like that. So I put this slide up with the optometrist's vision tool because of the testing and the measurement. But I always felt like they were playing a trick on people. Like, they're not playing tricks. What I mean is, have you ever gone through the thing? They're like, okay, is it better here or here? And then they'll be like, is it better on one or better on two, or better on A or better on B? And then they throw you a curveball and they're like, okay, or is it better on one or better here or better on C? And you're like, all right, you're just messing with me. Code officials shouldn't feel like that. Like, and I want the tools to be, you understand what the reference is. You're not comparing A to or better on two. We want to be able to compare what's in the reference home to what's proposed and be able to make sense of those things. So I'm going to move past that. That was probably a stretch of an analogy, but welcome to it. So there's a lot of content on this slide. And I just want to point out that what we're looking at for R405, here's our focus today, simulated performance alternative. So in this section, R405, we want to demonstrate that we're meeting it through the simulated performance. And we're taking this proposed design, and it has to be less than or equal to what would have been in the prescriptive and the mandatory section requirements of 401 through 404. And just to point out, 401 through 404 are the prescriptive pathways. So as long as you can prove that the energy use is less than if you had met the 401 through 404, you can still meet code that way, provided in the simulated performance path, or 405, you don't fall behind or past the backstop of the 2006 code. So what I love about this is that really it's the flexibility to show that it meets the overall code requirement by one of these paths. So this is where, just coming back to this point, that we're going to talk about this almost the entire remainder of the webinar. So if you hear proposed design versus the standard reference design 8 million times, that's about to happen. It won't be 8 million times. There's only like 20 more slides. But I don't want to do apples to oranges, but it's like, hey, we're proposing that we're going to have the middle avocado. It's ripe. So we expect its characteristics when it gets to final to have this firm, dark green color. If we get there, we don't want at final to have the actual results be that it was not ripe or that it was sort of like overripe. I don't know why the over meets, but there's definitely some. Oh yeah, that could be, maybe it's too leaky, or we went too light on some insulation value. But really, when you're thinking of a reference home, it's all the same thing. It's the same house, the same shape, same size. It's just characteristics are different. And then you compare the differences of those characteristics to decide, does it use more energy or less energy? So the real nitty-gritty of this, and I have another sort of version of this presentation that only talks about the table, the R405.5 table, and in the code book. So if you are flipping through your book at home, it's like Captain Kangaroo. We're going to go through our book at home. You'll find this table, and it includes everything that's in the reference. So when you are choosing your proposed, it gives you everything where you can compare, where can I do better than the reference? And when you're working with an energy rater, something that I do, we would do that comparison for you and sort of show like, hey, you are exceeding the reference in these areas, but maybe on these areas are the ones that you're falling short. So where could we find a balance so that the overall ends up meeting this performance path? I broke it down this way. There's like these 21 items. I was going to do like a blackjack slide here, but I couldn't find a good way of working that in. So there's 21 total items on this list. 5 of them, and we're going to talk about all of them, but 5 of them, you're not going to gain anything because the reference home is going to use what is proposed. It in the reference, it says it doesn't matter what you put here, it's going to match. There's another 6 items that go back and reference the table R402.1. And that's the table that everyone's familiar with that has all of the R values for your walls and basements, ceilings. Here's your insulation. You have R49 here and R20 here and R30 in the floor. That's the table. So this is what you can it compares to. Under the next 5, I grouped those into sort of like, there's a group that's like mechanicals or just measuring air. And then there's another 5 that I'll go over at the end that are either just less common or a little more involved, which is windows are somewhat involved. So I'm going to cover those last. So these are what we're going to get into next. And the gist of everything I'm going to cover is going to keep coming back to what's in the design versus what's proposed, just to give an idea of how these trade-offs might work. So, yeah, and it is the domestic hot water in here is one of these things that doesn't trade off. And the reason is because when you have the design and the reference, it's one of the things that's in, it's just items that match what's in the reference. So whatever you are proposing, it just matches the reference. And we're going to run through some other things that are in that same category. I have it highlighted in red in my slides for 2 reasons. One, because it's like, oh, you would really think that the hot water efficiency, like all the other things that have performance, would have been one that trades off, but it does not. It still impacts the overall use, the overall grand total of energy that's used in the analysis, which in the 2021 code could be a consideration. So, but just to talk about these other items, and again, there's a table that lists everything that's in the reference home, and this tells you what, if you propose something and you want to know if it performs better or worse, the thing that you compare it to is the reference table that's in the book, the table R4055. And these items, and these are not in the order that they are found in that table, they're in order by how I have them grouped. And this first group of 5 of the 21 items is items that just match the proposed design. So the reference and design are going to be the same regardless of what you put in. So for foundations, they are only looking at the type and the relationship to grade. So this is going to be for slabs. It's going to be the type and is a depth below grade. In the same way for a foundation wall that's sloping, like a slope to grade, which part's above and below grade and what's it made of. Internal gains, these are in there because it is the people. As people in the house, you're creating heat and you're creating humidity in the house, the appliances. So these are all internal gains that mostly when an HVAC designer is working on something and they're trying to figure out what they need for cooling loads and how much the occupants are going to offset the capacity. It's the people in the house. There's internal mass, which is something that's in an internal mass in the table isn't like a mass wall or a mass that's used as a thermal mass inside the house. These are things that can be moved around inside the house, like a couch or a waterbed. I reference the waterbed because if you had something like this and it was in a room that had a lot of sun exposure and you were heating the water, essentially that would act as an internal mass that would essentially have to come back into equilibrium later with the rest of the house. So it would be giving the heat back off to inside the house. We talked about service water heating. It's just looking at the size and the energy factor, and it just matches them to whatever you propose is going to be the same as what's in the design. And for the thermostat, what it's comparing is the set points. So you can't use the thermostat to use less energy. It establishes the set points, and you wouldn't be able to say, oh, well, in my house, it's going to use less energy. I meet the code because my occupants are only want it to be 60 degrees in their house instead of 72, I think it is, for the reference in the summer. So you can't say we're saving energy by changing the thermostat set point. So those things all stay the same. The next group all reference the table. So they're all going back to the table R4021.4, which has our various R values. So basement and crawl space walls. We have if we go back and look at the current code and think about this, we have to meet overall how things would perform under our current code. The backstop is just saying you can't do anything worse than that. So we're still comparing this to the current code table for the analysis. The backstop is only how far back you can go. So for our basement and crawl space walls, it's still using those prescriptive level above grade walls, the R20 or 13+5, the floors R30, the ceiling R49. So if you have to be worse than that, for instance, on above grade walls, above grade walls is a really good example just to point out a difference. So most folks are doing a 2x6 wall and they're putting an R21 bat in it. So the R21 bat is greater than what's in the table, which is only R20. So from a performance perspective, that already is going to be one of these criteria that's sort of letting you stockpile savings that could be used by having a lower value somewhere else. As long as you don't make it worse than what would be the total UA from the 2006. And that's cumulative. It really doesn't compare exactly back to the R19 that's in the 2006 prescriptive table because it goes by the total UA. But as long as the total UA isn't less than something that's in the 2006, then you are allowed to use it and use that as a trade-off. Opaque doors, same thing. It references the table with one difference that it says that there's only going to be 40 square feet of doors in the reference. So if you have lots more doors, that is something that essentially is going to reduce or increase your energy use because you've got more surface areas of the house that are only the R value of a door, which is usually less than what it is for a wall, usually around R5 to R6. R value for opaque door. So they're saying a front door and a garage door usually, basically, and that they orient that facing north. I put windows here, but we're going to come back to windows because it does reference the table for the U factor of the window and the solar heat gain. But there's a little more with windows when you're looking at simulated performance because it depends a lot on their orientation and overhangs. So we'll look at that. But those six, it's pretty easy to do the comparison. If you can do better than what's in the R402 table, that's going to help you. If it's some area that has to be worse than what's in the table, that's going to use more energy. The next five have to do with mechanicals and testing the air. So for mechanical ventilation, it's looking at the flow, how much air, and the efficacy of the fan. So when you're doing the comparison, you really want to be spot on with the flow rate because you're getting enough fresh air for the house, but you're not running the fan so often that it's actually impacting the tightness of the home. You're not adding it to the house's normal infiltration. Both the heating and cooling systems are things that trade off. So you would reference the R405 tables, heating efficiency and cooling, and compare that to what we have now is, typically a 95, 96 AFUE furnace and, into the 16 SEER, 14 to 16 SEER, pretty standard for air conditioning. A big one is the thermal distribution system and the duct testing. So the reference home is going to go back to the prescriptive values in this case. So the prescriptive value says you cannot be worse than R6. It's going to compare it against an R8 duct. But in the simulated performance, you can do things like deeply bury the duct. You can determine exactly what percentage of of the ductwork is inside conditioned space versus in an attic or in a garage floor. And by fine tuning that and getting exactly what areas are where in the house, often can have a very big impact on the energy use by specifying those things. Particularly the actual duct testing, where the prescriptive maximum in the 2018 is this 4% or 4 CFM per square foot conditioned floor area. If you go much lower than that, this can show that you're using less energy, especially with some of the duct testing, which is a leakage to outside test. So you get a total leakage test and a leakage to outside. And by proving that, yeah, there's some leakage in the duct system, but none of it leaks to outside the envelope, huge savings by not wasting that energy. And then, of course, the big one is the envelope, your blower door test number. In the 2018, we've dropped down to this 3 ACH 50 target for our air tightness of the building. So when you're achieving envelope that's in 2.75 or 2.5, all of that is way less energy that's being used, so that you have the availability to trade that off with something else. So the testing and of the systems is a big deal, along with the efficiencies of the heating, cooling, and the mechanical ventilation fan efficiencies. So these are the next batch that get a little bit into the weeds, and I'm going to be really good on time. I'm going to have to move it along. Let's do one more poll question, and then hopefully then I'll just speed the rest of the way through these. But this is a good place to take a break.
I think this is our last of your submitted poll questions, Mike.
Yep, this is good, because we just kind of talked about some of these things, and it lets me go a little more deeply when we get into the verification section. So I'm going to expand on this a little bit in the last section.
All right, responses are starting to pick up here. I'm going to leave it open for about 10 more seconds. Last call for answers. Alrighty. Shut down.
Which of these does not trade off with the performance path? So it's sort of a tricky question here, but the one that doesn't give you any kind of a trade-off is this total duct leakage. And the reason is, when you move out of prescriptive into performance, there is 2 values to the leakage of the duct system. What is how much the grand total leaks, and how much of the system leaks to outside. A good way of thinking of this is, you have a very large house. 80% of the ductwork is either in the basement or on the first floor, but because of this one little split level section, the easiest thing to do was to run 2 supply ducts into the attic, just so we could get some space conditioning. So 80% of the ductwork is inside the house. It's unlikely that it's leaking to outside. There's only 2 supply runs in an attic. Doing these performance path lets you test it and say, yeah, I had to do the test, but there were only 2 duct runs in the attic, and there was that tiny amount of leakage to outside. So the trade-off, and it's a trick question, but the trade-off is on the leakage to outside, not the total duct leakage of the system. So just to and thanks for that. I'm going to expand on the other ones briefly at the end. So back to our 21 items. These are the last of them. And vertical fenestration, otherwise windows, can be very involved. And I pulled a picture of a house that may or may not be built up in Willoughby, Ohio, just a little northeast of Cleveland. But this is a Frank Lloyd Wright house that has not yet been built. It was it's got a really cool design, and I had sort of found this poking around online and had done some work to model this because it's so nuanced. They may build this thing, they may not. I think that they may, which would be very cool. So have another Frank Lloyd Wright house to look at. But this is a really good example of a design that took advantage of everything that has to do with windows. The whole lower level, it's sort of like it's a split level, but to the far right of that picture is the south facing side of the structure. It has 12-foot. I think it was at least 10 feet. I think it was 12 feet though. There's transom windows above those windows that you can't see. But because of its design, this home would meet the 2018 code, and it's all concrete. The whole thing's concrete, but it's so effectively using the depth of the overhangs to take on the maximum amount of sun. The long area toward the left of the house is a hallway corridor that leads to the rest of the bedrooms. But that whole interior wall is sort of like a gallery walkway, but it allows in the summer the sun to get through those windows, heat the stone wall that's on the others that you can't see. And the same thing, the floor of the lower level where the majority of the windows are to the far right, it takes full sun the whole way back to the middle of the house into an insulated concrete slab that would allow this house to perform overall, meeting the code, and the windows are a huge impact. And so in our code in the 2018, what we're looking at, the reference is looking at the total area of the windows, and it's typically based on, it's going to have 15% or less. If you have a lot of windows, it's going to compare it against 15% window to floor area. So going over 15% is something that's going to hurt you. Having less windows, it's going to match. But if you go with a lot of glazing, a house with a lot of windows, it's going to be harder to meet performance path unless you have specifically designed it to take advantage of the windows through the orientation, through the solar heat gain coefficient. In this case, these would be very high solar heat gain because we want to get as much heat as possible inside the house. The U factor is another trade-off. And then these two, you wouldn't see at all in your prescriptive path, but it's interior shading fraction. And that's the amount of heat that gets past the blinds, essentially. So you have a factor that's how much of it can get through, and it's most of it, but they allow some trade-off for the interior shading, and then exterior shading is your overhangs. So windows can get a little involved, but it's amazing to see what can be done. The windows and shading orientation can have a huge impact on the overall energy use. Roofs and attics, really a big deal in performance path for hot climates, because you can put lighter colors on your roof and it'll reduce the absorptance, so you will take on less heat. Skylights are in there. They pretty much are always going to hurt you. The reason is that the design reference for skylights is none. So as soon as you start adding skylights, you're doing two things. One, you're adding additional wall areas that you see open in this picture. And I don't know if we can see how thick those walls are going to be, but I don't think we're going to fit an 5.5-inch bat in there. So typically you end up with these situations that you're adding additional wall areas that aren't insulated as well as the rest of the house, which is going to impact the use. Plus, the windows or the skylights themselves are being compared against what should have been the R49 attic insulation. So usually the skylights are hurting you. And a really sort of obscure one that we don't see a lot and just doesn't get modeled but can help in a cold climate is when you have this unconditioned buffer space, such as a thermally isolated sunroom. This creates an area that can be modeled and lets a wall be exposed to a lower delta T. So you get a lower temperature difference possibility. And it helps us in a cold climate because this room typically would take on some heat in the shoulder seasons, and we could use that for heating in the house. So moving very quickly through these last few slides, and I think I can do it in 9 minutes, Brian, and I'm sorry I won't have a lot of time for questions at the end, but I think we're doing okay. I like to look at this at different stages of construction, and the things that we are looking at here, what things that are being verified at different stages. There's quality of the installation. So not just what it's labeled, but how well was it installed. We're looking at ducts. We're looking at the difference between that total leakage versus the leakage to outside. For ventilation, we're talking about not just what it's rated to move, not that hey, this is a 110 CFM fan. I need to measure it and see how much does it really move. And the fan wattage can be compared against a worst case. So if you have a really high efficiency DC motor fan, it's being compared against essentially an AC motor fan that uses more energy. So you can gain by using a better efficiency fan. And then infiltration, of course, we talked about better or worse. I put that in red because I'm going to come back to that at the end. But generally speaking, less than 3, you're helping yourself to perform better. And currently, if it's greater than 3, you wouldn't be allowed because there is no trade-off for that. So at the design plan review stage of construction, it's good to look at these things because it can be an alternative to the prescriptive insulation levels. So why would I look at this at design review? For whatever reason, I can't get the full R49 or 38, whatever's required at some ceiling area. Can I go less than that? Sure. Let's compare it against this. Maybe there's those skylight walls. We just couldn't get the R21 up there. It had to be R13 only. Can we still get away with that? Sure. You have trade-offs that you can work with there. And deciding on this approach early on can be very useful in some cases for duct testing. And I gave the reference earlier. You might have a very, very large house with a tiny little bit of duct work in the attic, yet you're going to have to meet prescriptively a total duct leakage number, where if you approach this at final and you're just barely 1 or 2 CFM over the leakage value, it's not going to impact the overall performance that much. So going down the route of one of these performance paths might be the way to go. At pre-drywall, huge amount of work's being done here. So we're looking at the quality of the fully aligned air barrier and deciding on what things are going to help get from 3 air changes the whole way down to 2.5 air changes, so you can take advantage of that. The insulation grade needs to be also verified. You can't drywall a house, be halfway through the construction process, and then later say, well, gee, I guess I'll just go backwards in time and choose this performance path. If you do that, technically, you're using grade 3 insulation. No one has seen the quality of the install. So instead of saying it's grade 1, you would have to use a grade 3. So it's very important to grade and make sure you've done the proper installation. Same way with duct installation. You want that to be done in a way that's limiting the leakage, insulating it as well as possible. Sometimes a deeply buried duct in the attic versus just the insulation wrapped around it. And then ventilation ducts can play a huge role too, because if you've got a ventilation run with a lot of kinks and bends and twists in it, it is not going to move the appropriate amount of air. And when you're following a performance path, you can't go by what's rated. You have to move the correct amount of air. It has to be measured. So then we get into final testing. This is like the difference between Inspector Crusoe and Inspector Gadget. So now we're into the final testing of the house. But that's your blower door test, the actual measurement of this duct leakage to outside, actual measurement of how much airflow the fans are moving. And, and a question here, can you change your course midway through? And I alluded to that earlier. I mean, the answer is no. That's all I had for the joke, but the answer is no, but it's enforced differently in different places. Technically, you're supposed to state what path you are using at the construction permit stage. So when you're submitting your construction documents, it's not unheard of that it's been allowed in areas to be switched halfway, or could we look at it as more than one compliance path? I don't have the authority or a jurisdiction. The code official could decide that, but technically And the answer is no. You're supposed to state what path you're using in advance. So to wrap up, I want to look at sort of future code implications to the IECC, the 2021, which again, we don't know what will be adopted. We don't know how it will be amended. It's beginning deliberation now on May 2nd. So you can go to the Department of Labor and Industries Review and Advisory Council, or just search for the PA RAC, and you can get more information about that. But some of the most valuable things that I've seen from doing modeling, and all of this comes from doing energy modeling of homes. And for the code officials, what's important is getting the design and the reference. And if there are questions, you can go buy these two reports. Anyone that's doing a performance path can provide to you what is in the design and what's in the reference. And the reference are all these things that we just talked about, these 21 items. But those two documents are very readily and easily produced by the person doing this comparison and trying to see if it meets this performance pathway. The biggest thing that I see coming into 2021 is if adopted as is, there's a push toward having all homes with a continuous insulation on above grade walls, R20 plus 5. I have, I'm going to say 30% of the homes or more that I work with already are meeting the 2021 through some performance alternative without having to use the continuous insulation, continuous rigid. So that's a big deal as we're assessing these future codes. Another interesting point is this, where in 2018 they say, okay, you have to, here's your references, as long as it meets the these 2018 overall requirements, the energy uses at less, you can use that. In the 2021, they want it to demonstrate that it is all that and more. So it wants it to be, it meets the energy use of the 2021 plus 5% less. So you're only allowed to have 95% of the energy use or less in the 2021. And this was a interesting piece that, even though, and I've done this through some modeling where homes have been really, really close, it's interesting that one of the things that's been putting them over the top is the domestic water heating, because it can reduce the total energy use of the house down into a range where this 5% reduction is met. So even though it's not directly reducing the energy use, you can use something like a heat pump water heater toward the performance. So it's not a direct comparison, but Brian pointed out, he's like, that's very simple math used in a very complicated way. And it's like, that's a great way of saying it. But that's an alternative. So you can look to gain additionally by using hot water to reduce the overall energy use. The performance backstop is going to change. So in the 2021, you can go the whole way back to, as long as you're not worse than the 2009 IECC prescriptive. You can't go lower than that. Currently, we can go the whole way back to the 2006 code. When, if adopted as is, the 2021 would say you can only go back to the 2009. And a really big deal here is this possible trade-offs with the three air changes, where the performance paths as we move into the future may go to something that does allow you to go over 3 air changes. You're going to be penalized for going over 3, but you, as long as you are still demonstrating that the overall use. So if you're struggling at 3 air changes and the house is coming in at 3.21 air changes, but it still meets the overall performance, hopefully that is something that they'll bring into the code. So in short, and I know I'm going a tiny bit over, some of the benefits of the simulated performance path, we talked about this flexibility. Lower performance in one area can be made up with higher in somewhere else. It can reduce costs, especially with the continuous insulation. If you can meet it some other way and you don't have to go to continuous, it's great. And a huge benefit for me is that the extra work that has to verify these things really results in a great deal of additional quality assurance, which should result in peace of mind for the builders and reduced callbacks. Drawbacks here. I love this cartoon, but there's going to be more time up front because you have to do the energy model and figure out what you're going to decide before you start building things. That's very important. Like choose a path before you start building so you don't back yourself into a corner. There is some additional field verification that I mentioned, especially at pre-drywall, and there's going to be learning curve involved in going through a new process if you haven't done that before. So with that, I'll conclude and hand it back to Brian, and thank you, everybody.